Hi folks, we are starting the last day in our Unit 3 and we're wrapping up vectors with this lesson. And we are going to be talking about distance in R3. So we're going to look at a number of different things today. We're going to talk about the distance between a point and a line in both R2 and R3. The distance between a point and a plane, and the distance between two skewed lines. So the first thing we're going to start off with is the distance between a point and a line in R2. Now this is something that you could have done in grade 10, but now we're kind of expanding this to look at this in terms of our vectors. So in this diagram, we have a line with the Cartesian equation ax plus by plus c equals 0. We know that the normal vector to that line is the vector AB. And we've got a point, which is here P naught, which is X naught and Y naught. So this is the point that we're looking for, and we're trying to find this distance here from the point to the line. We know, of course, that always the shortest distance from a point to a line, we're going to want to look at the perpendicular distance. So I've created a right angled triangle in there, and we can label that D. So because we know in R2, we know that the normal vector is given by A and B, and that is a vector that's perpendicular to the line. That's going to be really important because we know that the distance along this path will follow the same direction as the normal vector. So we're going to use that to take a look at how to find an equation for distance here. One thing I think that it's fair to point out is that we can say pretty clearly here that the magnitude of vector P naught to P1, where this is some point on the line, so the magnitude of that vector there is the hypotenuse, and the magnitude of the distance, we could figure out distance over this equals the cos of theta. So cos theta, and that would be the distance. So the magnitude of the distance is equal to the hypotenuse times cos theta, because of course this distance would be on the adjacent side. Okay, so we're going to take a look at what that means in terms of finding an expression for this. Now the expression that we use that has cos in it is going to involve dot product. So we know that, kind of off as an aside here, that this vector P naught to P1 dot with the normal vector would equal the magnitude of this one, the magnitude of the normal, times cos theta. So these are the two things that we're going to use. So P naught P1 dot the normal would equal the magnitude of this times the magnitude of the normal times cos theta. So we're going to put together these two ideas and come up with an equation that we can use for distance. I'm just going to kind of clear myself some more space here, and we're going to use that to come up with the equation. So we know again that the distance over the magnitude of that hypotenuse vector is cos theta, so that D equals the magnitude of that vector times cos theta. Okay, now we also know that the dot product of this dot with the normal equals the magnitude of the vector times the magnitude of the normal times cos theta. And reading that a different way, we know that the magnitude of this P naught P1 cos theta equals the dot product divided by the magnitude of n. So I'm just going to divide out magnitude of n on both sides. And then I'll come up with two equivalent expressions. So now we can see that the distance we can write as this dot product divided by the magnitude of the normal. So D equals this dot product divided by the magnitude of the normal. Now I want to take a little bit closer look at the top of this because we can figure out an actual more simplified expression for this dot product rather than having to calculate it each time and determine a point on the line and determine the point that you're finding and do the vector between it and the dot product with the normal. So let's dive a little bit deeper into this piece here. So kind of off as an aside, this vector, we know that this vector here, P0 to P1, would equal x1 minus x0 and y1 minus y0. Okay, that's just using the endpoint minus the starting point. So I can do the dot product of that with the normal vector, which is AB. So then I get ax1 minus ax0 plus by1 minus by0. Now, I know that this section here ax1 plus by1, I know that that is a point on the line. So since that is a point on the line, so since x1, y1 is on the line, ax1 plus by1 plus c equals 0, and we can write that also as ax1 plus by1 equals negative c. So I'm going to use this and sub it back in there. So we're just simplifying an expression for that dot product on the numerator of my distance formula. So this is going to be negative ax0 minus by0, and instead of this, I'm substituting in a negative c. I'm going to factor out a negative there. And because I know that distance has to be positive, I can actually eliminate that negative. So we're just going to take the absolute value. So this is an expression for the dot product, but I always want a positive distance. Like if I get a distance of negative 12 units, we just say, oh, well, it's 12 units away. The direction is not something that we're really concerned with here. So I'm going to plug this back in at the top for that dot product as negative ax0 plus by0 plus c over the magnitude of the normal. And then I'm just going to actually take the absolute value because I want to only get a positive distance. And I can drop the negative sign because we don't know whether it'll end up positive or negative. So basically the distance formula in R2, you're going to be taking the point, the x0, y0 point, and basically subbing it into the equation of the line as your x and y value, taking the absolute value of that number and dividing it by the absolute value of the normal. which can also be written absolute value. The magnitude of that normal is the square root of a squared plus b squared. So that's the equation that we're going to use for the distance from a point to a line in R2. So using that equation, we are going to take this distance equation, so the magnitude of a x naught plus b y naught plus c over the square root of a squared plus b squared. So we have an equation here of a line and we have a point. So my point is going to be my x naught, y naught, and my a and b values are the coefficients of x and y in the Cartesian equation in R2. So we're just going to find the distance by using this formula that we came up with. The distance is going to be the absolute value of -5 times -2 plus 7 times 3 minus 1, that's my c value, over the square root -5 squared plus 7 squared. So here I get -10 or positive 10, 10 plus 21 minus 1 over the square root of 25 plus 49. I'm going off the page there. So here I get the absolute value of 30 on the top, which is just 30. Remember, with an absolute value that you would take any negative number and just switch it to a positive over the square root of 74. And you could rationalize that denominator, or if this was some kind of word problem where you were looking for an exact value, you could do put that in on your calculator and round it off to 2 decimal places. So next we're going to take a look at the distance from a point to a line in R3.